In this video, we will be talking about the light-independent reactions, which is module 2.3 of our quarter number 4. Now, we do remember from our previous discussion that we have finished on talking about the stages of photosynthesis. As you already know, there are two important stages of photosynthesis. One is the light reaction, and the other one is the dark reaction or the light-independent reaction, or Calvin cycle, which we will be dealing with in detail a little bit later. Now, before that, do remember that there are four important things that happens in the light reaction. Number one is that light is absorbed, the energy of light is absorbed by the chloroplast through the thylakoids, particularly through the photosystem 1 and the photosystem 2. Second important thing that happens in light reaction is that the water is split into oxygen and hydrogen, wherein the electrons are extracted to replace the excited electrons from the special chlorophyll. The third important thing is that the ATP is produced, and the fourth important thing is that NADPH is produced. Now, do take note that the ATP and the NADPH will be important because it will be needed for the Calvin cycle. And also take note that the most important thing that happened in the Calvin cycle is that carbon dioxide is fixed so that you can produce carbohydrates or sugar. Now let's go dive into the details of the Calvin cycle. First of all, we know that there are three stages of the Calvin cycle, CRR. First is carbon fixation, second is reduction, and the third is regeneration. So these are the three important stages of Calvin cycle. And then in order for us to memorize be familiar with the carbon cycle, do take note of this important information. Number one, the number of carbons of the molecules must be taken note of. Second, thing that will be helpful is the placement of the phosphate group. So take note which particular carbon they would be attached to. And then the naming convention will be based on the number of carbons and also on the placement of these phosphate groups. So with all those helpful things, now go straight into the cycle. Now, first of all is the phase number one, or the first phase, which is carbon fixation. So what happens here? There are a number of important actors here. One is the RUBP, the other is the Rubisco, and the third one will be carbon dioxide. So what happens here? Number one, please take note of the number of carbons. If you take a look at the RUBP, you will have 1, 2, 3, 4, 5 carbon. Now also take note the placement of the phosphate. The first phosphate is connected to the carbon number 1, while the second phosphate is connected to carbon number 5. That's why the name of this molecule is ribulose 1,5-bis phosphate. The ribulose, the 1,5 will be pertaining to the position of the phosphate on carbon 1 and also on carbon 5. The bis will be pertaining to two phosphates present, while the phosphate would be pertaining to, of course, the phosphate group. So its name is ribulose 1,5-bis phosphate. Now this RUBP will now be catalyzed using Rubisco as the enzyme in order to react with 3 carbon dioxide, so that 3 copies of RUBP reacting with 3 copies or molecules of carbon dioxide produces 3 copies or 3 molecules of a 6 molecule or carbon molecule, as you can see here. You can see the original RUBP 1, 2, 3, 4, 5, and then the carbon dioxide would be attached to the second carbon. Now please do take note that this intermediate molecule is very unstable, so it will be automatically cut in half, producing 6 copies of 3 carbon molecules. Now please do take note that the phosphate is found on the third carbon, as well as the other side on the third carbon as well, so that the 3 will be pertaining to the number of the carbon number where the phosphate is connected to, phospho of course to the phosphate group, and glycerate is related with the 3 carbon molecule. So the name of this molecule is 3-phosphoglycerate 3-PGA. Now take note, this is now carbon fixation phase. On the second phase, so before that, do take note of this one. You have 3 copies or 3 molecules of RUBP and 3 molecules of carbon dioxide reacting with each of the RUBPs. Because of that, each of the 3 will now be become a 6 carbon molecule, which will be split in the half, so that each of this would contain a phosphate and another phosphate here. So you have 1, 2, 3, 3 PGA, 1, 2, 3, 3 PGA, 2 copies resulting from each of the RUBP plus carbon dioxide. So that 3 copies of RUBP or molecules of RUBP produces 1, 2, 3, 4, 5, 6 copies of 3 PGA. And that's the whole thing about the carbon fixation phase. Now, as we go to the next phase, which is the reduction phase, do take note two important things will be happening here. The addition of a phosphate group because of the usage of ATP, and the addition of a hydrogen, which changes the conformation of the molecule with the use of NADPH. Now, let's go straight to the reduction phase. So we ended up with 3 phosphoglycerate, 3 PGA. Now, do take note that there is only 1 phosphate group on the third carbon, and there is a need to add another phosphate on carbon number 1, so that since there are 6 copies of phosphoglycerate, we have 6 copies of ATP needed in order to extract phosphate, and then you will be putting that or attaching that to the carbon number 1. Now, since the phosphate will now be in carbon number 1, as you can see here, the name changes so that it now becomes 1,3, the 1 pertaining to the phosphate on carbon 1, and the 3 pertaining to the phosphate on carbon 3, 1,3, bis pertaining to 2 of those phosphate, and we have phosphoglycerate. So it now becomes 1,3 phosphoglycerate with phosphate on each side of the molecule. Now, with the addition of NADPH, the phosphate on the first carbon will now be removed. That's why an inorganic phosphate will be produced here. And then the H will attach itself to carbon number 1, producing an aldehyde. That's why the name will be changing. It now becomes glyceraldehyde 3-phosphate. The aldehyde, the glyceraldehyde, will be pertaining to the aldehyde form here on the first carbon with the removal of the phosphate, while the 3-phosphate will be pertaining to carbon number 3 containing the phosphate. So you see here, glyceraldehyde 3-phosphate. So from 3-phosphoglycerate, there are 6 copies of this, an addition of phosphate to each of these 3 molecules or 3 carbon molecules. You now have 1,3-bis phosphoglycerate. The addition of the hydrogen on one of the phosphate removes it, producing 6 of this inorganic phosphate, and then producing 6 glyceraldehyde 3-phosphate. Now, take note that you have 6 copies of this one of the G3P will then go out of the Calvin cycle because this one will be used for the production of glucose and other organic molecule. Now, let's look at the changes in the molecular conformation. You have here the 3-phosphoglycerate with the carbon 1, carbon 3 containing the phosphate group over here, and then a phosphate will be added on the first carbon. So you now see it here, and this is the change that happens here. So this energizes even more the molecule, becoming 1,3-bis phosphoglycerate. And then the phosphate will now be removed with the addition of the hydrogen from the NADPH, so that the phosphate becomes inorganic phosphate and removed. And then the hydrogen will be here producing an aldehyde. That's why its name becomes glyceraldehyde 3-phosphate or G3P. So I hope you were able to take note of this. Now, after this, we are already done with the carbon fixation phase and the second phase, which is the reduction phase. We now go to the next one. Take note that there are now 5 of this. Take note, 1, 2, 3, 4, 5, 6. Prior to that, it now becomes G3P with the addition of ATP. Take note that there are now 5 G3P remaining because one of the G3P removed itself from the cycle so that it can be used for the production of glucose. Now take note of this. If this will be G3P, 5 copies are there, and there are 3 carbon for G3P. 1, 2, 3 times 5 is 15 carbon. Notice that the RUBP, there are 3 copies of this, but there are 5 carbon for each. 1, 2, 3, 4, 5 times 3 is also 15. So you will see here that the G3P there are 15 carbons in total, later becomes RUBP, which also 15 carbons in total, which means that the G3P, by some means and some reaction, they will now be rearranged so that they will produce 3 copies of the RUBP, and that will be the regeneration of RUBP. Do take note that in order for that to happen, 3 ATPs are needed in order to regenerate the RUBP. And here's the molecular picture of that. So you have 1, 2, 3, 4, 5 G3Ps plus 3 of the ATPs. Then it will produce 3 copies or molecules of RUBP. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, etc. So it will now be producing 3 RUBPs. Right. Now, take note that one of the important things you have to take note of is the number of ATPs produced, the number of NADPH produced. So take note, the total of ATP will be what? 6 over here, 3 over here, 6 NADPH will be produced. So that's why we have this question, in what phase of the Calvin cycle is NADPH required? So you're very familiar already that it's in the reduction phase, as you can see. And going back here, this is where NADPH is used. Another question, for every carbon dioxide that enters the cycle, how many ATP and NADPH are needed? As we have already taken note of, the answer to that is, for 3 carbon dioxide that entered the cycle, 6 ATP plus 3 ATPs are needed, total of 9. So for every 3 carbon dioxide, 9 ATPs are used. And for every 3 carbon dioxide, 6 NADPH is needed or used. That is why for every 3 carbon dioxide you will have 9 ATP and you will have 6 NADPH. But the question is how many per carbon dioxide? So you simply have to divide. So 9 divided by 3, for every carbon dioxide you will need 3 ATPs used. For every carbon dioxide you will need 2 NADPH. So this would be the ratios that you have to remember. Now of course, if you have, for example, 4 carbon dioxide, then you just have to simply multiply that. So for example, 4 carbon dioxide, how many ATP and NADPH produce? So you will do is 4 times 3, you will have 12 ATPs. 4 times 2, you will have 8 NADPH. If you're asked how many ATPs are produced when 5 carbon dioxide will be entering into the system, now you will simply multiply for every 1 carbon dioxide. Since you have 5 times 3 is 15 ATP, and then 5 times 2, then you have 10 NADPH. So it's very easy to compute for that. Okay, how about this question? For every glucose synthesized, how many ATP and NADPH are needed? Now you have to first know how many carbon dioxide would be needed to produce the glucose. Take note that for you to produce the glucose, 6 ATPs would be 6 cycles, would be needed, or 6 carbon dioxide will be needed. So the answer to that is, okay, going back here, 3 ATP and NADPH. If for every 1 glucose, 6 cycles are needed, or 6 carbon dioxides are needed, so we now have 6 carbon dioxide for every 1 glucose, and you have to multiply 6 times 3, it now becomes 18. 6 times 2, it now becomes 12. So for every glucose, you will be needing 18 ATPs, 12 NADPH, because 6 carbon dioxide needs to enter the Calvin cycle in order to produce 1 glucose. So if you're asked how many ATPs are produced for 2 glucose, then you have to multiply everything. 2 glucose, then it becomes 12 carbon dioxide needed. 18 times 2 is 36 ATP needed, and 12 times 2 will be 24 NADPH needed. So that will be the way to answer such question. So again, 6 Calvin cycles are needed because 6 carbon dioxide needs to enter the cycle. 18 ATP, 12 NADPH will be consumed in the 6 cycles in order to produce 1 glucose molecule. And that ends our discussion.